I'm Saurav. I work at Melbourne Epicenter. It's an epidemiology center at the interface of Royal Melbourne Hospital and University of Melbourne. But I won't talk about my daily life and daily work. I'm going to talk about something else, which is in time series. Okay, so how does usual time series analysis begin? It begins we collecting data, probably at regular intervals of time. That is, from a time series, we observe or sample the time series at regular intervals, and then the first step we do is we assess whether or not the time series is second order stationary. Now, why do we do that? Because once we can ascertain whether the time series is second order stationary or not, then it opens up to us a universe of models that we can then fit to estimate and forecast our data into future. That's all good, and that's why there has been intensive research on modeling, on testing, and construction of a lot of statistical tests to ascertain whether or not a time series is second order stationary. But now consider this, the other world, the world of non-stationarity. And we all know that non-stationarity comes in diverse colors, and I've just given 4 examples here. The panel, the top left panel, is a time series that displays non-stationarity in mean. The trend increases with time. Panel B, we have data from stock markets, and it displays non-stationarity in volatility. Panel C is an example of a data that we can observe from earthquakes or landslides or geological events, where the time series may be otherwise stationary except for the event time or when we approach or immediately afterwards when it receives a shock, and then we have non-stationarity. And then we have a 4th option that we can consider. Again, this is overall a non-stationary time series, but in finite or small windows of time, the data displays second order stationarity. Now, faced with this wide spectrum of universe of non-stationarity, if the domain expert then asks you that I'm not interested in that dichotomous classification of the time series into stationarity or otherwise, could you rather provide me a tool that I can use to assess or measure the non-stationarity of a time series? Is that possible? So to do that, we have to set some baselines or benchmark. Let's begin with the definition. And I will stick with what second order stationarity is and how we can study the deviation from that. Now, time series YT observed at regular intervals of time, or you might even consider initially looking at a discretely observed time series. It's called second order stationary if it's constant with respect to time in its first 2 statistical moments. That is, the mean is constant, the variance is constant, and the covariance measured at 2 different points in time is simply a function of the difference of the 2 time points. That is second order stationarity. So this gives us a baseline upon which we can try to measure our deviation. So if second order stationarity means invariance with respect to time, if we could somehow measure the variation from this constancy in time, we may have a way to construct a tool to explore the non-stationarity. So I come from a model-based paradigm in statistics, and for illustration of the tool here I've chosen the DLM framework. One of the reasons for choosing DLM is it can describe, or it can be used to describe or estimate a wide range of non-stationary time series. Many of you in this audience might know what a DLM is. In time series literature, it's also called a state space model. It's described by a coupling or intertwining of 2 sets of equations. You have the observation equation YT, which is what you observe, but the observation equation is driven by an underlying system equation or a latent sort of equation, theta t. It's the theta t that will control whether or not the process can become stationary, or whether how non-stationary it can get. So, for example, if you put a value of, say, any value, any constant value for GT between 0 to 1, such that W is also 0, that is the system variance is 0, and GT is a constant between 0 and 1, then you get back the usual AR1 process. Okay, and we will see a few other variations of this. So I have a DLM or let us suppose that the time series that I have can be either approximated or generated from a DLM. One of the objectives of a DLM modeling then is to estimate the posterior mean of theta given the entire past. Once you know the posterior mean of theta, you can use this posterior mean to construct the forecast mean, and based on these two things, then you know the entire state of the system at time t given its entire past. Okay. Now, that posterior mean, I've called it MT. It's a noisy object. So if I am to study the variation of this noisy object with respect to time, it's going to be very difficult. So what I suggest is we smooth, or we interpolate this noisy object with an interpolant. Here I have used non-parametric regression, and it's a very well-known penalized spline equation. So the thing is this: I fit smooth function GT to MT with respect to this penalty factor. But once I have fitted the smooth function, I no longer restrict myself to MT. Instead, I study GT, which is a smooth surrogate of MT. And I call this second component, which is the penalty factor, as a measure of non-stationarity of this time series with respect to this particular statistical moment. Okay? And why do I call that? SYT, it's the integration of double derivative of that function. So we know a double derivative is curvature of a smooth function. So this one can be considered a cumulative curvature of that trajectory, whatever trajectory you are measuring with respect to time in that finite interval. Okay? So in this sense, so SYT, or this penalty factor, is measuring the rate of change of gradient of this particular statistical moment in any finite window of time. And in this sense, I'm saying that this measures the second order non-stationarity of the process with respect to this particular statistical moment. But this is not restricted to either the model or the particular statistical moment. In fact, this principle can be easily extended to studying any functionals of an underlying stochastic process that you can construct with respect to time. SYT is a non-negative index and increases with increasing temporal variability of the underlying statistical moment. And our basic conjecture is this: for two different time series, YT and XT, observed over the same intervals of time, if SYT is greater than SXT, then we will say that YT is more non-stationary than XT, in the sense that YT varies more rapidly in time than XT with respect to that statistical moment that we are studying. And if the process is close to second order stationary, then we would expect that SYT is very close to 0. Okay, so, and now we'll go to see some simulations. But before simulations, we have also constructed bootstraps, which can be used to study the non-stationarity of the, which have been used to study the uncertainty of the non-stationarity measure, and we'll see that as well. To do the bootstrap, we have again the DLM infrastructure available to us. Once we have the structure, then this can be exploited to construct residuals, and from the residuals you can resample and create pseudo data sets, and based on that, for each data set, then you can construct your mean function, or the posterior mean function. For the posterior mean function, you can have the GT. From GT, you can construct the non-stationarity measure. And you can keep this as many times as you want, and based on those bootstrap replicates, you can construct confidence bands or histograms, or you can study the uncertainty of the non-stationarity measure in your time series. Okay? And we can do some more. We can study the mean squared errors as is commonly done, and so on and so forth. Now, the penalty function itself, it's a very simple function. It only requires you to mention the time varying trajectory. You can mention the posterior mean, you can mention the variance, whatever you want, and it does its thing. It depends on the FDA package. Its still not in CRAN. I have not put it there, but sometime this year I plan to include that or distribute it as part of the LOCITS package. But I'm also happy to just, if you need it, just write to me. I will send it to you by an email. All right, so now on to some results. So on the bottom panel, you see the measures corresponding to stationary time series. Time series is stationary when W, the system variance, it is 0 in the DLM modeling framework, and GT stays between 0 and 1. Okay, so both the bottom panels are stationary time series models, and for them we see that S, the parameter S, it stays largely close to 0. On the other hand, when we have non-stationarity parameters, either we fix W or we fix GT, and then we see as the other parameters increase, I don't know what I did, oops. Okay. As the other parameters, as the other parameters increase, then we have increasing value of non-stationarity. We have done some more parametric sort of simulation where we play with different functional forms for GT, and these are the functional forms. I think it's still readable. So the first model is a stationary AR1 model, and then we bring in different functional forms for GT for a finite value of W, that is the system variance, and for each such model we compute the corresponding non-stationarity measure. And we can see that for the stationary model, it's very, very small, of the order of 10 to the power minus 17 or so. For the other models, it's clearly non-negative. And in this particular simulation, we see that the sinusoidal GT gives us the highest non-stationarity index in this case. And on to Bootstrap, once again, we see similar things. The non-stationarity measure is very close to 0 for a stationary time series or a second order stationary time series, and it keeps increasing as the time variation in the posterior moment keeps increasing. Again, finally the same Bootstrap in histogram form, and we have done 5,000 replicates. The top panel is the bootstrapped non-stationarity metric for an AR1 process, and I will argue that SYT, or the non-stationarity for AR1, is highly concentrated around the value 0, while for the others, or the non-stationarity models generated by the other DLM models, we see that SYT stochastically dominates the SYT of the stationary time series. Okay, so a couple of applications. So in time series, we have this classic problem of distinguishing two time series, or how we can classify two time series separately. So we have a classic data set that's available from Stoffer and Shumway's book. So the problem is whether or not we can classify an earthquake data or distinguish an earthquake data from an explosion data set, and I would argue that SYT, the non-stationarity index, gives us different signatures for the two different time series computed over the same intervals of time. In this case, the non-stationarity measure has been computed at non-overlapping windows of length 100 all the way till time 2001. I wouldn't go into more descriptive details. I just want to finish with this other last application. So at University of Melbourne, now I am currently collaborating with a geology group, and they want to monitor the life of a landslide. So here you have the velocity measures that are being tracked as the landslide goes on. And the red, if you can see the red line, yes, the red line is the spline, and then I'm studying the non-stationarity of the spline. The only difference in this case is I'm studying the non-stationarity on a moving average basis. So this is clearly overlapped non-stationarity measure. So, and that has been recorded in this last panel plot. And wherever you see bumps are regions where the underlying geological zone has it has undergone a change. And when I presented this back to my collaborators, they said each of the bumps that have been identified by the non-stationarity measure, they actually represent some scientific events that happen and that they know from physics has happened to that particular landslide. So it was quite a nice thing to see. I'm now integrating this metric as part of construction of a statistical algorithm to monitor landslides and hopefully more generally for other geological phenomena. I think I will skip the other bits and just conclude here. So we have proposed a descriptive tool that's fairly generic. It has its limitations, by the way, which I didn't have the time to go through. One of the limitations is clearly that if the time series has linear trend, this tool will not be able to pick up. So what we suggest is if you have a linear trend and you know that, you take a first difference of your time series and then apply this tool. There can be other things, including the moving window or what should be the length of the window. Questions like those also arise. The other question is, if I have two different time series measured in two different scales, and it's quite natural that they might throw up two very different values, how do we deal with the scale issue? So what we suggest is if you are studying both the time series in the same time window, you should scale it by its standard deviation. One single standard deviation so that you preserve the structure of the time series and yet you make it scale free, and then you apply your non-stationarity metric on that scaled time series. We have also described a Bootstrap methodology. So if you are estimating your time series using a DLM, you can very easily construct non-parametric Bootstrap to measure the non-stationarity, measure the uncertainty of the non-stationarity metric. We do have some applications in earth sciences, but I'm happy to hang around and chat if you have more ideas on how you can use this. And I don't plan to write a package just for this, but I will make most of the routines available through the LOSITS package of Guy Nason, but I'm happy to send the codes to any of you guys if you are interested. In August, we have a forthcoming conference of the Statistical Society of Australia, and if you are around, come over for that talk. Over there, I will present a very different approach to measuring or estimating non-stationarity. And before I finish, so I essentially live in this area, Royal Melbourne Hospital and University of Melbourne. Much of this work, it began when I was a postdoc at University of Bristol with Guy Nason. My current collaborators are in University of Melbourne, and I have benefited immensely from the funds of Guy Nason and my current boss, Sanjay Paul, who receive funds from EPSRC and NHMRC respectively. So with that, and this is the paper if you are interested in reading up. And thank you, I'm happy to take some questions. I've not. One of the things we wanted to do is we didn't really want to go into testing. The space to compare. No, but I've not done that. No. But perhaps the most definitive way of studying a deviation from non-stationarity would be to apply this metric, for example, on the spectrum. The spectrum is the signature of a stationary time series, or second order stationary time series. So if we construct a time varying spectrum and apply this on that tool, that may be another way of looking at it, rather than DLM model fitting.